So we know that we're going to be producing some water that has a mass of 18. So the peak at 18 must represent the water. And notice that that comes after the reaction, which makes sense because that's supposed to be a product. Okay. And we know that we have carbon dioxide. Well, that has a molecular weight of 44. So the line at 44 must represent the carbon dioxide. And it also makes sense that that only appears after the reaction because that's another product. We know that we're using oxygen as a starting material. Well, diatomic oxygen has a weight of 32, so the line at 32 must represent the oxygen, and it makes sense that that only occurs as a starting material. That occurs before the reaction, not afterwards. And then the other line must be this. So what the other line was at 32? So we know that the molecular weight of this must be 28.
Yeah.
Because that's the only number that's left.
Right.
The only number that we haven't already assigned is the 28. That means this must have a molecular weight of 28 grams.
Okay.
Because that's the whole that's what mass spectrometry does. It figures out the molecular weight of things. That's the purpose of mass spectrometry. It's a technique for figuring out things' molecular weight. So we know that something here had a molecular weight of 28. Well, that's got to be the hydrocarbon because all the other peaks have been assigned.
So here you would write 18 water, 28 mystery hydrocarbon, 32 we said it's O2, right? So oxygen, gas, and 44 is carbon dioxide. You got that one?
Yeah.
Okay.
So far so good? That's part A?
It's exactly like what you just did. Do it. Do it.
B,
yeah.
D, okay.
We're working on part B now?
Mm-hmm.
Yes.
Okay.
So
I kind of have a
ABC,
question.
it'd be CH2.
Yeah, so the key thing here is that the peak at 18 has the same height as the peak at 44. That means that we're producing equal amounts of carbon dioxide and water. So maybe 1 mole of carbon dioxide and 1 mole of water. So this is just the same as the previous question that we did. So that would give us maybe 1 atom of carbon over here and 2 atoms of hydrogen over here. But this only tells us the ratio. For all we know, we could have gotten 2 and a 2 over here, and that would give us a 2 and a 4 over here. But now we figured out the empirical formula for the hydrocarbon, which is CH2. And that's the answer to part B.
Isn't it? Well, I guess that would be the empirical formula, but
You're confused because there was excess.
because you get a molecular weight. So I'm thinking, do they? Well, I guess.
It sounds like maybe you're moving on to part C.
Yeah, so it'd be C2H4 for C.
Yeah,
so CH2 would be the answer for B.
This is the empirical formula, because by definition, the empirical formula has the ratios in lowest possible terms. So even if you knew that the molecular formula was C2H4, that's not the empirical formula. The empirical formula has to reduce to lowest terms. Now, what would be the weight of CH2? That would be 14.
Yeah.
Well, we know that can't be the molecular formula because earlier on, we'd already figured out in passing that the true molecular weight here is 28.
Okay.
So we need to double this to get a weight of 28. I think you guys already know that if you know the empirical formula and you know the molecular weight, you can combine those to find the molecular formula. Well, that's what we just did here. In part B, we figured out the empirical formula, and we'd already known the molecular weight from the original mass spectrometry printout. It tells you the molecular weight is 28. That's the whole purpose of mass spec. So we can combine those now. So remember, even if you know the molecular formula is C2H4, that doesn't mean the empirical formula is C2H4. You got to reduce to lowest terms. So you got to make sure you're answering the right question. It would be easy to give the molecular formula when they wanted the empirical, or give the empirical when they wanted the molecular, especially if they only ask for one of those. So it's good to double check when you're doing the test.